Yes, the fun part, principal component analysis. Let's first consider quadratic forms. We'll go slow, so you will have time to understand what's going on. And for quadratic forms, we have a function, vector function f of x. It takes a vector as an input and returns a scalar, like a single number, and it's defined as x transpose ax, and A is symmetric. In 2 dimensions, just to go slowly so you understand what's going on. We have A defined with just 4 values because it's symmetric. B and B are the same, A and C don't have to be the same, and we have some vector x and y. Let's multiply this through. First, let's compute A times x, and which is this, ax plus by, bx plus cy, a vector. That's fine, but now let's multiply ax by x transpose, and we're getting a polynomial in x and polynomial in y, quadratic. So when A is positive definite, then this quadratic form is a paraboloid and the level curves are ellipses. So level curves are when this function is fixed to a certain value. So when it is, then we'll get an ellipse. And side note, a matrix is positive definite if and only if all of its eigenvalues are positive. So let's look at an example. Let's take an A, which is symmetric and has the same values on the diagonal. X transpose AX, quadratic form, then equals 5x squared minus 4xy plus 5y squared. Okay, fine. But this is an equation of an ellipse. And the interesting part that if you look in x and y, the ellipse is tilted. But if you look in the y, in the u and v, the principal axis of the ellipse, then of course ellipse is let's say flat. Let's look at a multivariate Gaussian density. So here it is. Expression K is the number of dimensions and C is a K by K covariance matrix. Don't get scared yet, we'll get to explaining each term. So in the bivariate case, 2-dimensional covariance matrix is variances of x, y, and cross covariances of x, y, and well, cross covariance of x, y, and notation note. Sometimes people write sigma squared, but that's the square. This is already the second order. That's just a slightly different notation from sigma squared because we have multidimensional case, and I want to stress which dimension we're talking about. So note, if C is symmetric and positive definite, then C inverse is also symmetric and positive definite. Can you prove that? Okay, pause here, try to prove it. Okay, I'll help you. If C is positive definite, then we have this. We can diagonalize it. But then C inverse, well, actually we can diagonalize C if it's symmetric. Now we know that all eigenvalues, all diagonal elements of lambda are positive. Then C inverse is nothing but inverse of the lambda. And inverse of the lambda is a diagonal matrix, is nothing but 1 over lambda 1, 1 over lambda 2 for all of the elements. Also a positive definite matrix because all of the eigenvalues, new eigenvalues, are still positive. The scale will change, but yeah. So covariance matrix. An n by k covariance matrix X, where nth row is the nth sample of a Gaussian distributed random variable. This. Each row is a sample from two-dimensional Gaussian. For example, yeah, k equals 2, but the dimension here could be any, and the number of samples correspondingly will require more samples depending on the dimension. But just think about this. Now we have data samples from a Gaussian distribution arranged in an X matrix as rows. Covariance matrix. To go to covariance matrix, let's talk about the sample mean of all of those samples. Sample mean of all of those samples is nothing but an average of all of those rows. And we will assume for now that mean is 0, sample mean is 0, because if this is false, we can always make it true by subtracting mu from each of the samples before constructing X. For covariance matrix, observe that if we take our X matrix and transpose it, then each column in X transpose is a sample, and each row in X is a sample as before. But that means we're just taking outer products of those samples and summing them up. This is the same as in spectral decomposition. Now that we know that X transpose X is just a sum of all of the outer products of the corresponding samples, we take one sample, X1 and Y1, because we're in a two-dimensional space. And as you remember, we scale this by X1 and scale this by 1, 1, Y1. And that's what I wrote here. Just multiplied each vector here, multiplied through, and we do that for each sample from 1 to n. Good. So, but what is this for a zero mean vector? Sum of all of the x's is nothing but an expected value of the product, corresponding product. But expected value of the product is by definition our covariance, or variance in this case, and cross variance or cross covariance. in the off-diagonal case. So our 1 over n x transpose x is an approximation to the true covariance or a sample covariance. That's not all. So let's talk about isodensity surfaces. We're still in the Gaussian distribution, and the level surfaces of the multivariate Gaussian distribution, g of x, consist of those points where g of x has constant value. Right? So we have a distribution, and distribution is not a paraboloid. But still within that distribution, there will be isosurfaces or level surfaces for distribution of a constant value. Just an example for one-dimensional case of Gaussian, there will be a point, well, 2 points for Gaussian when it is symmetric to have the same value. But now let's go into 2 dimensions. And we'll see if we just put a level surface or level plane that there will be many points that will have the same probability density value or the same value of the Gaussian distribution. And it follows that level surfaces are ellipsoids because if we equate Gaussian density to some constant and then take a log and rearrange, we will see that those level surfaces are described by a quadratic form where the right hand side is a constant. So an ellipsoid has principal axis. For a sphere, any basis, any orthogonal basis forms those principal axes, but for geode or kind of squished sphere, we already have pre-selected axis. We can't select anything else but this red C axis, although A's can be, again, anything you can rotate in this plane. And once you squish this ellipsoid again, now you have defined all 3 principal axes because they're not equivalent anymore. They're just defined by the geometry of the space. So principal axis theorem. The principal axes of the ellipsoids forming the level surfaces of the multivariate Gaussian distribution are given by the eigenvector of its covariance matrix. This is covariance matrix of a Gaussian distribution, and principal axes are eigenvectors. And as usual, we sort in descending orders our eigenvalues and place the corresponding eigenvectors in correspondence to those eigenvalues. 2-dimensional case is easy. So in a 2-dimensional Gaussian, any level surface will be an ellipsoid, and if we take the largest eigenvalue, it will be here on this axis, and the eigenvector corresponding to that eigenvalue will define the major principal axis of that ellipsoid, and then the minor will be eigenvector corresponding to the smaller or smallest in the 2-dimensional case eigenvalue. So let's try and diagonalize covariance matrix. That is, let's try and find are similarity transform. So because the covariance matrix C is real symmetric, and if we have enough samples full rank, let's assume that we do, it has k orthogonal eigenvectors, and it therefore can be diagonalized as follows. Well, we've seen that before, where kth column of W is the eigenvector of C with the kth largest eigenvalue, and D is diagonal with the corresponding eigenvalues on the diagonal. So DKK is that eigenvalue. Okay, so we can take C, the covariance matrix, and diagonalize it using eigenvectors decomposition. So KL transform. KL transform is let me. So KL stands for Carhonian love. Let's try. Yeah, Carhonian love transform. So we can represent the samples of the Gaussian distributed vector random variable x in the basis formed by the eigenvectors of its covariance matrix C. This change of basis is termed Carhonian love transform or KL transform. So we can take each of our samples and project them into the basis of the eigenvectors. So U is a representation of x in the basis formed by the eigenvectors. For example, by what will we achieve by that? Imagine we have this narrowish covariance matrix. So there is a point here. There is a point somewhere here, and it's expressed by x1, x2 coordinates in the canonical basis. If we project it into the basis of the eigenvalues of this covariance matrix of this these samples, then we will have a large x and close to 0 x2, a large x1, or let's call it w1 and w2. Right? It will be a convenient representation. Most of them will have non-negligible w1 value and close to 0 w2 value. So that's KL transform. And the question is, what is the distribution of the U of the KL transformed Gaussian variable? Well, let's look at it. It is still multivariate Gaussian with covariance matrix D now. But covariance matrix D is diagonal, as we know. So it's easy to see in the bivariate case what happens. So since T is diagonal, and it's related to our covariance matrix by similarity transform, each the determinant in this case, in two-dimensional case, you see is a product of the diagonal elements. And inverse is very simple. We've already discussed that just a couple of minutes ago. Is 1 over the elements of the diagonal, and you can verify, multiply through d1 by d, and you'll get an identity. And so now let's consider Gaussian distribution with diagonal covariance. In two-dimensional case, if we look at the Gaussian distribution and multiply through the quadratic form here, that is the expression we get for two-dimensional Gaussian distribution with diagonal covariance. Oh, but wait, it is diagonal covariance, this distribution. Oh, but it's decomposable. We can just write it as a product of two exponents. And look what happens. It's decomposable into a product of two exponents or two distributions. Both of them are Gaussian. That means Gaussian with diagonal covariance is separable, and we can represent it as a product of distribution that corresponds to each of the random variables of that Gaussian. But this means, since the joint distribution of u and v can be expressed as the product of distributions of u and the distribution of v, we say that u and v are statistically independent, and knowing the value of u tells nothing about the value of v. So after KL transform, the variables in our Gaussian become statistically independent. So we'll often use regression test or linear fit for that. Imagine here we have nice statistical dependence in this axis or in the spaces. But then after KL transform, the variables along the axis for the Gaussian distribution are independent. Okay, what we need to look at is example usage of all of this linear algebra, which is fantastic, by the way, and it's good if you can understand it and visualize it in your head.